is a professor in biosciences and biomedical engineering at Indian Institute of Technology, Indore. He is also a tenured professor at Biological and Ecological Engineering Department at Oregon State University. In fact, very recently, this year only, he joined. And Dr. Murthy's research is broadly focused on sustainable bioprocessing. Professor Murthy's group works to develop technically feasible, economically viable, resource sustainable, environmentally less impactful, and socially acceptable technologies. They extensively use system analysis tools such as techno-economic analysis and life cycle assessment. He is a world-renowned scientist in his area, and we are happy that he has come back to India to serve the nation, and he is now at IIT Indore and will be available for graduate engineers and for any kind of interaction and discussion. He is very, very pleasing and a smart guy, and anytime you can approach him. This is in brief, and a very good friend of mine. Thank you. Dr. Murthy, please.
Thank you so much, Professor Indramani, for that very kind introduction. And very good evening to all of you, both online on Facebook and here. And especially, I would like to thank all the students. And one of the reasons why this topic, life cycle assessment as a tool for sustainability analysis, this is an area of research that we have done. And it is something that we as ag engineers are uniquely qualified to do. Because one of the things that we do is we take a systems perspective very, very naturally. That comes very naturally to us. So that is what I'm going to talk about. So can we move on to the next slide, please? So basically the goal of this presentation is to provide an introduction to this life cycle assessment. And at the end of this, I hope you can understand the importance of the systems analysis, understand the LCA process, and then describe how the environmental impacts are calculated, basically using the life cycle assessment method. So next slide, please. So what is systems analysis for sustainability?
Dr. Murthy, sorry. I think
yes,
I would like you to go slow, please, because
sure, no worries.
This is an important topic. I think all are very much keen.
No worries.
Please go slow.
Sure. So what is systems analysis for sustainability? So when we talk about, this is something, the systems analysis is a word that you'll hear very, very commonly these days being spotted everywhere. In fact, you'll see that in the corporates, you'll see that in the governance, you'll see that in the policy making, you'll see that increasingly in the literature. And when we talk about, this was something that used to be called holistic approach and systems analysis. So taking that approach for sustainability, essentially what it means is, so we need to take multiple perspectives for analyzing any technology or a process or a product. So taking the techno-economic analysis perspective, so looking at the technical feasibility, economic viability, and then the environmental impacts, for example, what are the resources required? For example, this is something that we ag engineers know really well. So for example, to grow crops, we need land, we need water, and these are not that easily appreciated by others, while we very intuitively understand this thing. And then the policy and the social political issues, these are all really important things. So when we talk about the systems perspective, it is really challenging and it requires multidisciplinary approaches. And these are not something that you can add on. These are needed at the core of basically when we do the systems, take a systems perspective or systems analysis. So what does that mean when we apply that to the sustainability? So I'll go to the next slide, please. So again, elaborating on that systems analysis once more, is that normally we think of, especially in engineering, classical engineering, let's say you take a mechanical engineer or a chemical engineer or an electric engineer. There the idea and problems and solutions are much more linear. So there is a goal that you want to achieve something, there is a situation, so essentially that defines the problem, then we try to take a decision and essentially try to implement something and we get the results. So this, whereas the systems thinking as defined by the Richmond in '94 is the art and science of linking structure to performance and performance to structure, essentially, so putting that in the largest perspectives. And one of the key things that happened was, going to the next slide please, is something that comes out of the systems perspective is the synchronous effect. Remember all that 2008 economic crisis, That led to the energy crisis, and that led to the food crisis in a lot of the many parts of the world. So that is an example of many systems where each of the stresses in one part will actually result in a systemic crisis. Right now, we are exactly living in such a systemic crisis. Remember what happened is, right now, a simple virus coming from coronavirus coming from a basically from China is impacting. It's basically a health issue for many of the people, and right now that has transformed, that is interacting to cross the intersystemic boundary into the economic system. Now we see the lockdowns to prevent that, essentially the spread of this virus. That has led to huge impacts on the basically the economic systems, and it has led to huge stresses in the economic system all over the world. And now, if you have read the news yesterday, Trump has said, basically, President Trump in the US has declared that there will be no immigration. Now you see how that is moving on into the political aspects of things and also the social aspects of things. So now the immigrations will be impacted, and then that will result in all kinds of political situations. So this is the example of what we call as a synchronous effects. So moving on to the next slide, please. So on the next slide, I basically was trying to show the overload of the food systems and the overload of the energy system that happened in 2008. But right now, as we just discussed, this is right now happening. Something that is bound in the health system is impacting our economic system, and that is leading to a systemic crisis because these interactions cross over. And this is exactly what we study in our systems analysis. So moving to the next slide, please. So when we talk about different sustainability, so when we try to use these approaches for assessing the sustainability, why is sustainability important? Because we want to maintain something, basically sustainable production systems, sustainable and resilient production systems. And because, as we know, we are increasingly living in a world which has very less resources. We have increasing population. And when we talk about that, such a situation, we need to be more sustainable and resilient. But whenever we talk about sustainability, a lot of things are very vague. So we need kind of specific metrics to assess our progress, for example. So typically the sustainability in the industrial context is talked about in three aspects. So the society, economy, environment, and the ecological indicator. So today, what we will be talking about is the third one here, the environmental aspects. So how do we assess sustainability from the environmental perspective? So what we mean by that is we are trying to really see what are the environmental impacts of a product or a process. So let's say think of a biofuels production. So let's say we are growing corn, as in they do in US. So what is the impact of that on the environment? So that is something that we want to try and learn, and that is where the life cycle assessment is a very good tool to do that. And this is comprehensively used in many of the companies. And whenever you see a product being said that it is environmentally friendly, it is green, basically what they are trying to do in the background is they are doing an LCA and then comparing that to an existing process or a product and then telling you that this is better than that. So moving on to the next slide. So LCA is a basically method to assess the environmental impact of product, processes, or services. But it is very, very important to remember that this is not a risk assessment. So risk assessment is separate. So for example, if you do an LCA for a nuclear power plant versus a coal power plant, just to give you two examples. So it will not, LCA will not give you the risk in both of them. So obviously nuclear power plant will have a higher risk than a coal power plant in terms of catastrophic failures. But then environmental impacts is something that coal power plant will be higher. And so that is what the LCA will really assess, the environmental impacts and not the risk assessment. And also, LCA is not something that will tell you anything about the performance or the cost analysis of a process. So it is important to do the techno-economic analysis separately, do the risk assessment separately, and the environmental impacts through the LCA. And most often you will see two versions of this LCA. One is called attributional life cycle assessment, and the second one is called a consequential life cycle assessment. The attributional life cycle assessment is typically used when we are looking at a specific farm or specific process industry or things like that, whereas the consequential LCA are much more used in the policy making. So we will mostly focus for today's discussion on the attributional. And there are different variants that people talk about. Cradle to grave. Cradle essentially involves all the way from the production, manufacturing, use, and disposal. That is the cradle to grave. Whereas the cradle will involve the recycle of the process in addition to the disposal. So essentially, when you close that loop of production, manufacturing, use, and disposal, and the recycle, that is the cradle to cradle. Many times, the industries will use what they call as cradle to gate. So for example, let's say you have a tractor manufacturer. So they will be trying to assess their processes in their factory, and they don't want to really be responsible for how the user uses the tractor. So then what they do is they will look at all the processes starting from the production of the tractor to the gate, factory gate, and that is what this cradle to gate LCA is. So this is kind of a partial LCA and typically used in many industries. And well to wheel is a very specific type of LCA that is used in the transportation fuel sector. And so this is very commonly whenever you see biofuels, LCA, environmental impacts of biofuels and stuff like that, this is the this is the type of LCA that is being used, well to wheel. This essentially refers to oil well to wheel of the car or the vehicle, essentially. So moving on to the next slide, please. So one of the key things that an LCA is designed to address is the shifting of the environmental burden. So for example, if you look at a hydrogen car, just look at it and then you say, okay, hydrogen goes in, the water vapor comes out, so there are no emissions. But then to produce that hydrogen, you have to burn fossil fuels that emit CO2. LCA is specifically designed to prevent basically the shifting of the environmental burden. For example, in this case, from the hydrogen in the hydrogen car to the fossil fuels. So in the hydrogen production process. So there we define 3 types of flows in the LCA. So the first one is called elementary flows. These are the critical things for an any LCA. The elementary flows are basically the flows that come to or from the environment without any modification. So for example, think of plants absorbing CO2 in a farm. That is that flow of CO2 into the plants is an environmental flow. Irrigation water that we put in is an environmental flow. The runoff from the field is an environmental flow. Whereas basically some of the product, let's say we are trying to grow some rice. So that would be an intermediate flow. And if it ends up in a rice processing plant and finally we harvest paddy, that goes to a processing plant and we get rice. Final product rice is the product flow. Paddy moving from the farm to the processing rice mill is the intermediate flow, and elementary flows are the CO2 that comes in, the water that comes into the production facility, and those kind of things. So that is where basically those are the 3 flows: elementary flow, intermediate flow, and the product flow. Moving on to the next slide, please. So the attributional LCA, as we just briefly discussed earlier, will talk about the total emissions for a process during the life cycle of a product. So this is very, very important for a process or a product, or when we look at it in isolation from the complete system. Whereas the consequential LCA looks at is what is the change in the total emissions from the process. And today, essentially, we will be talking about the attributional life cycle assessment. So moving on to the next slide, please. So life cycle assessment has 4 steps. The first one is called goal definition and scoping. The second step is called life cycle inventory. The third one is called life cycle impact assessment. And the fourth one is life cycle interpretation. We'll go through each of these steps in a little bit of detail. So, but let's go back, go to the next slide, please. If you look at what is really behind this whole thing, what is this magic that people talk about when they talk about LCA and all? Actually, process is very simple. So I'm going to give you the background of that. When you see basically the math that takes place, you'll see that it's pretty straightforward. So this is the most commonly used method called the matrix method of LCA. So what is it? Essentially, we have something called a technology matrix, and which will relate the processes to the different relationship among different processes. So for example, let's say we are using the rice mill I was talking about, uses 10 kilograms of paddy to produce 9 kilograms of rice. So that relationship is described in the technology matrix. The demand vector is basically what we want from the system. So let's say we want 100 kilograms of rice. That is that vector F, demand vector. The scaling vector is the one that we use to scale the technology matrix to get the demand vector. So if you represent A don't worry about it if you are not following this right now. We have an example, and that I will share with everyone, and we'll go through that also. So this technology matrix A dot S dot product is equal to your demand vector F. So now, oftentimes we don't know the scaling vector S. So what we do is we invert the matrix A, technology matrix A, to get S is equal to A inverse F. Now there is something called a unit emission matrix B, which essentially defines how much are the emissions, different types of emissions for each of the processes that we described in the technology matrix. So then what we do is we take the unit emission matrix and multiply that with the scaling matrix, scaling vector that we got, to get what we call as emission inventory vector. And then finally, there is something called a characterization matrix Q, which will basically say what are the environmental impacts of these emissions. So essentially, the technology matrix describes the relationship between the processes. Unit emission matrix B defines the relationship between the process and the emissions. The characterization matrix Q defines the relationship between the emissions and the environmental impacts. So as you can see, for getting the environmental impacts vector, which we call as H, you have to multiply the Q, the characterization matrix, with G, which is the emission inventory vector. So when you simplify that, essentially you have Q dot B dot A inverse into F. That's it. So we have a demand vector, we have Q, B, and A inverse. So typically what we get is basically this, there are 4 steps I was talking about. The technology matrix is the second step of the LCA, that is your life cycle inventory. The third step, which is the impact assessment, is essentially multiplying Q into B, and to get your final, basically the impact assessment impacts, and that we actually. So that is essentially, in nutshell, the whole process there. The biggest challenge that we have, we spend about 70% of the time defining that technology matrix. And there are a lot of studies that we use in, from literature and scientific studies to develop this unit emission matrix B. And then the characterization matrix is one of the impact assessment methods that we can use, and that is typically formulated based on some kind of hand waving. So that is where a lot of uncertainty is. So moving on to the next slide, please. So when we talk about the first step in the life cycle assessment, the goal definition and scoping, we need to really, so having that mathematical background here, we need to really think about what are you going to use this LCA for. So we define typically in terms of what we call as a functional unit. We have to have that description of these products, processes, and the system boundaries. And we have to have the clear quantifiable goals. And what is, for example, one of the things that we need to know is what is the system boundary? What are the resources available for a study? Because you can do an LCA in about 3 hours. You can do an LCA in 3 months. You can do an LCA in 1 year. Basically, it depends on what kind of resources are available and what is the required specificity. So if you are just trying to compare two processes when just to see, you may require to do that in like 3 months. But if you just want to see that offhand, like yes or no type questions, so that you can do it in like few hours. Whereas if you want to really do a detailed analysis to formulate a policy, for example, California did that for their low carbon fuel emission program standards. There they did like multi-year studies of different pathways to get that information. And how should the results be displayed? These are some of the things that we need to think about. Going on to the next slide, please. So for example, let's say you have a process here. So one of the things that we try to do is we try to identify what are the processes that we need to include in our LCA and what are the processes that we can exclude. Because getting information for each process, getting the emission factors for each process is a tremendous job. It takes a lot of time and effort to do that. So ideally, we would like to have as minimum number of processes as possible to get the maximum specificity, maximum information out. So we try to play that, balance that thing by using what we call as a RMEE, system boundary method. So this stands for relative mass, energy, and economic system boundary. So essentially we use that to draw the system boundary. So as you can see here, we have a main process that has two upstream processes, processes 1 and upstream process 2. And then the upstream process 1 has inputs from upstream process 0. So going to the next slide, please. So each of them have different inputs. So as you can see, we normally set a cutoff percentage. So we say, okay, RME cutoff percentage is 5%, let's say. Then we calculate the mass, energy, and the economic value of inputs to each of these processes compared to our functional unit, the product that we are interested in. When we calculate that, if the mass, energy, and the economic value of an input, all the inputs to a process are less than the cutoff, we ignore that process. If it is more than the cutoff for even one of them, we include that process. This is a very systematic way of doing things. So I will be sharing these slides so you can go through this in more detail. So you can see that thing. So moving on to the next slide, please. So once we do that goal definition scoping, then we do the life cycle inventory. This is the step that takes about 70% of the time. And that is the most time-consuming step in the whole LCA. And we have to collect input data based on different standards, and we have to check for all whether that meets the ISO standards 14044 as defined in that 14044. We need to look into the energy, raw materials, other inputs to the process, all products, co-products, waste streams, all releases, and all the environmental impact aspects. So once we do that, essentially, then we basically have completed the inventory. Moving on to the next slide, please. So oftentimes, especially in our processes, so for example, we have co-products that are produced. So if I'm going back to that example of paddy in a rice mill, in addition to the rice, we also produce rice husk. So that is a co-product that is produced. So how do we allocate for that? Here I have shown an example of a corn dry grind process, which produces ethanol as a main product, but also produces DDGS, which is distillers dried grains with solubles, as a co-product, which is used as animal feed. So there are many ways to account for these co-products. And going to the next slide, there are three different methods. One is called based on the mass, energy, price, and displacement. So basically the mass, energy, and price are pretty straightforward. So you look at the main product, that is ethanol in this case, the price of that or the mass of that, the energy content of that, and compare that to the energy, mass, or the price of the co-products, in this case DDGS, and based on their ratios, you calculate this ratios, you allocate different share of emissions. So here, for example, DDGS is about 46% of the total mass. So we basically say, okay, 46% of the total emissions go to DDGS, rest of the stuff goes to basically the ethanol emissions. So system expansion is a little more complicated, where what we are trying to do is we are trying to see what is this product used for. For example, if DDGS is used as an animal product, animal feed product, then we try to see what is the product that this is replacing and then go for it. So similarly, for an example of rice husk, if rice husk is being used as a energy source in, let's say, the brick kilns. So if the rice husk was not there, they would have probably used other biomass or coal. So we say, okay, it is replacing coal or something, therefore we need to consider the emissions of the coal and allocate that to the rice husk, because that is the application of it. So once we complete this process of allocation and life cycle inventory, then we move on to the next step. Next slide, please, which is called life cycle impact assessment. So here we have, for example, from our life cycle inventory, we know how many kilograms of CO2, methane, or nitrous oxide, or sulfur dioxide, or hydrochloric acid, or different things come out per functional unit of the process based on all the inventory that we did. Now, typically you will have hundreds of these things. So you'll have, in a typical LCA, you will have about 120 to 150 such numbers. So it is very difficult to interpret that number. So then what we do is, we take that and then try to model for different environmental mechanisms. So for example, the CO2 will, if it is emitted to the air, we know that it causes basically the global warming effect. So we actually look into that thing and then say, oh, okay, one molecule of CO2 will cause so much rise in the temperature, whereas one molecule of CH4, methane, can cause up to 25 times the heating effect, based on the same environmental mechanism that we're looking at. Therefore, the environmental impact of CH4 in terms of the climate change category or infrared forcing or the global warming potential is 25 times more than the base molecule CO2, which is used as a reference. Similarly, if you want to look at the acidification, so we use sulfur dioxide as a reference. Now we say, okay, Now, sulfur dioxide, so many kilograms of sulfur dioxide in air is 1 unit. Now compare that to nitrous oxide emissions and then say, okay, it will cause acid rains. So what is the impact there? And we try to come up for those what we call as midpoint indicators. But even these, you typically get from about 150 numbers in the LCI, you get to the midpoint indicators. There you get to about 6 to 12 indicators, midpoint indicators. But sometimes even that is too much, because if you are a corporate or some kind of policy maker trying to communicate these results, if I give a dozen indicators, it's very difficult to formulate a policy. So what people do is they will take additional models for environmental mechanisms and then get to what we call as endpoint indicators. For example, human health or ecosystems in terms of species loss per year, or daily, which is basically disability adjusted life, loss of life in years, things like that, different indicators like that, which will basically be used to form the score. So essentially this process that you're seeing here is that matrix Q that is in action here. Okay, so moving on to the next slide. So when we finish the life cycle impact assessment, that is where most of the studies will stop. But then we have to, typically if we follow the ISO guidelines, we have to do the next step also, which is called life cycle interpretation, where we look at the results and try to identify how complete they are, what are the sensitivity, how consistent they are in terms of the analysis, and then based on that we come to conclusions, especially talk about limitations and the recommendations are presented. So this is essentially the 4-step life cycle assessment basically process. Moving on to the next slide, please. So there are a few important terms in LCA that we need to remember. The first one is called functional unit. Essentially, this is the measure of the function of the system that we are investigating. So this is the one that this is basically the quantity or the unit which we use as a reference for basically measuring the inputs and outputs are related. For example, I have given here as 1000 megajoules of bioethanol or 1 kilogram of plastic. And going back to our example of a rice mill with paddy as an input and rice coming out as an output, we could say one metric ton of rice produced is one function. So then we evaluate how much paddy is required, how much husk is produced, everything in relation to that 1 metric ton of rice grain that is produced. So the net energy value is another important term that you'll see, especially in the transportation fuels, bioenergy area. So what that basically tells you is the energy in the functional unit minus the fossil energy used to produce it. So you see that little diagram there that says fossil energy is E1, the energy contained in the biofuel is E2, amount of renewable energy coming in from the photosynthesis or wind energy or hydropower or however it is E0. So E2 minus E1 is what we call as net energy value. When we take that as a ratio, E2 divided by E1, we call that as net energy ratio. So obviously, as you can see, the net energy value must be greater than 0, so that there is actually some energy advantage in the biofuel, or the net energy ratio should be greater than 1, so that we actually have this more energy is produced. So think of this as investing in a stock market. So for every dollar or every rupee that you invest, you want to get more than 1 rupee back. So in this case, you are looking at it from an energy perspective. We are putting in 1 unit of fossil energy, we want to get more than that back, because there is this contribution of the renewable energy, E0. And obviously that process is not completely efficient. That's why these energy ratios are important. And sometimes we use what we call as the equivalent numbers. So essentially this is a normalization that we use for different factors. Remember that example of methane and CO2 I was trying to give, that 25 times more effective greenhouse gas than CO2 for methane. That 25 times is the equivalence. So essentially 1 unit of methane will be considered equivalent to 25 grams of CO2 equivalent for measuring the global warming potential. And so this is essentially some of the terms that you want to remember. Going to the next slide, please. So one of the things that you'll find really in the literature and in all kinds of things is that you can do an LCA, and many times it is like statistics. Various LCA analysis are very different in terms of the results that they get. Primarily, some of the reasons are that they use different system boundaries, the data quality, accuracy, how they allocate the co-products, the nitrous oxide emissions. And this is something very, very important for us as ag engineers, because I will show in the next few slides that the ag production side is really important when we look at anything that involves biofuels or bioproducts. Agriculture is the most critical things. Yeah, and then there's this indirect land use change, and then different reported units that we use. Now, talking about that importance of agriculture, why we need to talk about it, going to the next slide, please. So many of the LCAs that people do are basically done by chemical engineers, and they focus mostly on the processing and the conversion part of things. But if you actually look at the 3 steps, so feedstock production, processing and conversion, and the distribution. So I have compared that here for biodiesel and ethanol, 2 biofuels. So when you look at it, there is about 57% of the total greenhouse global warming potential is produced in the feedstock production stage for biodiesel, and about this 68% for ethanol. Water use, about 93% of the water is used in that feedstock production stage. And basically for ethanol, again, about 70%. And cost, 70% cost, about 70% cost for biodiesel, and about 50% cost for the basically the feedstock production. On the other hand, if you look at distribution, so the global warming potential, water use, or a cost, they're about less than 5% in most cases. So what this, and then whereas the processing and conversion, it is important. You'll see that the global warming potential is about 42%, 30% in that range. But water use is again 7 to 31%. So yeah.
Another 3 minutes, please.
Sure, yeah, we'll summarize it, yeah. So essentially, you'll see that the feedstock production stage is very important. That's the point that I want to make this here. And as ag engineers, we are uniquely qualified to go into that stage. Why? Going to the next slide, please. One of the things that we found in many of our research things is that not only the agriculture, how we do the agriculture, whether we are going for no-till, high residue, whether we are doing the common practice or reduced till low residue, and whether we do it in different locations, all these things have an impact, which we as ag engineers can very well appreciate. Going to the next slide, please. So what can we use that for? All these LCA results, we can actually use that to produce these kind of maps. As you can see, we are trying to produce these maps which show different emissions of GHG emissions of under different practices. NT is the no tillage, TT is the common practice, essentially, conventional tillage for camelina biodiesel in some parts of Oregon. You see the parts which are red, those are parts where the emissions are higher than diesel actually. So essentially what we can say from this is not all locations are suitable for biodiesel or biofuels production. And this is something that we as ag engineers can use the LCA tools to effectively quantify and basically come up with very good recommendations for producing any kind of feedstock in the country. Going to the next slide, please. This just shows the impact of allocation methods. To finally summarize, going to the next slide, please. Summary of the process steps, we have 4 steps. Goal definition scoping, life cycle inventory, life cycle impact assessment, life cycle interpretation. And so these are the 4 steps. Please do remember these 4 steps. And going to the next slide, this is a bunch of links that I have provided. Next slide, please. That basically you can look into different software that we use and stuff like that. And this is example of dry grind corn process and with the matrix method. And I will be, I want to request basically the moderators to share the Excel sheet with all the participants or post it somewhere so that they can actually go through the calculations, stuff like that that we have produced. And there are some questions for discussion if you want. And with that, I would like to thank everyone for patient listening. Thank you so much.
Thank you, Dr. Murthy. And friends, you might be feeling a little different from automation agriculture, but our purpose is to explore different tools and agriculture as such, and agricultural engineering, most of the processes are system engineering processes. And Professor Gajendra Singh is here, who introduced this subject at IIT. And he will brief, and he basically brought it, in the beginning, that how, and including his PhD thesis, etc., was on this. And this is high time that we should use these, tools, important tools, new tools for solving our problems. And I will basically encourage you to get in touch with Dr. Murthy. And whenever you are planning some research, even your students are planning for research on some topic, this tool, that is tool must be understood and applied in your research system and for solving problems. And he told numerous examples also. And thank you, Dr. Murthy, for sharing this. This is your expertise area, and since you are in India and you are in Indore, so it will be nice that if my friends, because networking of people is another aspect of this webinar. So I will be thankful if you are open enough to interact with them in future when they contact you through on phone or through email. And please guide them to introduce the tool. This is task for you, that introduce this tool that of studying system engineering in India with this latest tool. Thank you very much.
Yeah, just on that note, Professor Indramani, I'm very open and I will encourage, in fact, I would like to encourage all ag engineers to take lead in this kind of things, because this is something that we can do. And one of the things is, even now, it is very sad that we have to use European-based databases for analyzing Indian agriculture systems, and which is very something that we should not be doing, and we should actually produce. I know that we produce a lot of data that we can actually have our own database of, for the life cycle inventory, conducting life cycle assessments and things like that. And I will be conducting a short course on techno-economic analysis and life cycle assessment for about 6 days at IIT Indore sometime once this lockdowns and everything will be done. This will be totally be a hands-on course which will teach the tools and for conducting both the life cycle assessment and the techno-economic analysis. And it is open to all PhD students, any students basically. And I would highly encourage our ag engineers to come and please attend.
Thank you very much. That's what the purpose actually. Sure. Thank you. Over to Dr. Sayyed. Professor Singh, please, if you can, very brief.
Yes, I think both the presentations, really excellent presentations. First one, I would like to say the Om Prakash did a wonderful job of explaining the steps in a very systematic way, in a very simple language. My suggestion will be that when we have two different topics, we might have to think about like first hour for first topic and questions followed up, and then the second session of the second topic like Ganti did on other one. I was very impressed by what Ganti was talking about. That's what my whole career was. I started agriculture systems analysis, agriculture systems engineering at IIT. So I'm very happy that those things are so progressed and recent. And life cycle assessment really is a very, very useful tool being used now in everything. I think even ICR institutes are being asked to utilize this tool for certain assessments. So I'm very happy. Both presentations excellent. We have excellent start.
So I think, thank you. That's what we thought in agriculture engineering, which people don't know, many of the other areas, that also we can include in this. It will give, otherwise people will be bored on the same topic somebody is talking about. So probably a mixture will make people alive a little bit. And like we planned, we will have only about, the training program will be around 45 minutes. So within that time, it will be boring for some people who doesn't want to know it. But so we want to keep it a second part, and first part is the people who can come. Or we can change also if there is people think about it, we can change the timing slot also. First and second.
We might have to discuss with the presenter how much time is presentation and some minutes for the question answer. Yeah.
Yes. I think the question answer, I saw the first one, there were some questions. And now I think somebody, SK Satpati is there. I hear, raise the hand. Can you please make him to speak, Mr. SK Satpati? Yeah. Can you ask your question? You raised your hand. Can you ask a question? He's not a panelist. He's in the. attending. Mr. S.K. Satpathy, you have any question? Vijay Lapsetwar, you have raised your hand. Can you enable Vijay Lapsetwar? Can you promote Vijay Lapsetwar into the panel now?
Hello.
Can you
Hello?
include him in panel so we can see his video?
Can you hear me?
Yeah, I can hear you, Vijay. Setu, can you promote him into? Can you bring him into the panel so we can see his face? Okay. Now we can see Vijay. Because Vijay Lapsetwar, I know. I want to see his face at least. He's a good of irrigation, and actually I should thank him frankly. He was the guy when I was running with 12-13 branches. It's about 20 years back. He came to me saying that he introduced me to meditation, Vipassana. I'm indebted. Please, Vijay, go ahead.
Thank you, Sayed.
Your question.
My first observation on Dr. Om Prakash, one of his slides talked about training aspects. I'm of course from water resources side. In my very big general expression, that
can you have your video on? Can we have your video on? Possible? You can turn it on the video.
Oh,
you don't have. No problem.
Oh, I'm sorry. Yeah, is it okay now?
Now we can see. Yeah, now others can see you.
Right.
Thank you.
Well, sorry about that.
Because yesterday GDG told we have to see the people.
Yeah. In general, when we talk of training in water resources, it is highly neglected. It is conducted by spare people for the spare by trainers in their spare time. Something has to be done about training in general. It could be in agriculture automation or in water resources, but unfortunately it's not happening. I don't know if some of you are aware of the Water and Land Management Institute at Aurangabad, which is in its last dying stage, I would say, because the Department of Water Resources has handed it over to Department of Soil Conservation. And you can imagine what does the Department of Soil Conservation has to do with water resources training. Another example is ICWOM in Australia, that is International Center for Excellence in Water Resources Management. It's in Australia. The government of Australia has withdrawn its fund to ICWOM, which is basically a training core institute, from last month. So that is also happening in the international area also. So this training is something is required in every field of the study, and it needs to be looked at it. Observation for Dr. Murthy, of course, LCA is not for cost analysis, but just to flag, there is something called value engineering. And that value engineering is a similar kind of diagnostic tool which evaluates different projects, different processes, and ends up in proposing the huge cost saving in all kinds of projects. Thank you so much. Thank you.
Okay, I see Mr. Debendra Barua wanted to have a question, something. So
yeah,
please
this is. Hello, am
I
audible?
Yes, you are very much audible.
Yes.
Please.
Thank you very much. I got this information about the webinar from a friend of mine, and immediately I joined. I was a few minutes late, but I'm very much benefited. I congratulate the ISA team, particularly Singh sir and the Ramani's team as well as you. I must only one observations, or that is compliment to Murthy regarding that LCA. And I wish the ISA will take a lead to generate the data. Really, inventory and data on Indian condition is really a problem. And we are also doing a bit work on it, particularly while comparing the different energy system. And we do not have our own data, own inventory. And for that matter, we need to rely on the data generated or created in other places. And that is really an inaccurate assessment. For the sake of assessment of two systems of LCA, and if we do not have our genuine indigenous data, and that is really a need of the hour, and I hope it will come, and I will really benefit. I congratulate. Nothing much to add.
Okay, thank you. I think we'll come to the second part of it. Before that, I want to make an announcement. Those students who are there or want